Are you guys able to hear me fine? Okay, awesome. So these devices are definitely not made for people with hair or dresses because I'm putting all types of contraptions on just to wear this thing. So if it flops around a little bit, just don't judge me for it. I am from Lightbend. You may have heard of us, you may not have heard of us. We're the corporate stewards behind the Scala language, Lagom framework, the Akka toolkit, Play framework. We are heavy contributors to Spark, especially Spark streaming, and all of our APIs are, unbeknownst to some people, available in Java. We have 2 headquarters, one in San Francisco, one in Switzerland, and pretty much we're all over the world. I won't bore you with the details of this slide, but if you've heard of the Reactive Manifesto, a lot of that was born out of the founders of our company. And so, very quickly, a little bit about me. Picture worth 1,000 words, so these are some of the things I like. Travel, skydiving, I like aerial views, and the things I don't like are heights, which doesn't match with my love of aerial views, and I don't like clickbait, those weird ads that you see in your newspapers and such. And so I figure with the amount of data that they collect about me, they should never ask me how to fix my fatigue with, I don't know, that looks like lemon or something like that, so I hate that. But anyway, why are we here? Why are we talking about event sourcing, CQRS? What does that even mean? And to be honest, the title of this talk really assumes a couple of things. One, it assumes that you know what event sourcing is or you care about it. It also assumes you care and know about CQRS, and you think that either or both of these things is useful in some way. The title of the talk also assumes that you may have come here to see something that's 20 minutes long, which if you're anything like me, my attention span would love a 20-minute talk. So this is not false advertising, but we will be talking about event sourcing in Akka in a 20-minute span within a longer time period, okay? So, what about event sourcing? What about CQRS? Why is this thing suddenly blowing up? Why is it suddenly called a new buzzword? And the truth is, it's not actually very new. It's semi-new in the enterprise because a lot of people are just hearing about it. It seems like it's an emerging thing in the enterprise. But the ideas behind this are very old, and they're actually very useful, tried and true ideals. But suddenly, within the enterprise and within lots of other places, it's time to update your legacies again. So this whole app modernization field that people are going through, it's happening again, and this time we're modernizing for what? The cloud, right? We're modernizing for the cloud, we're modernizing for this IoT economy or this next economy that you see that's coming up. And this time we're building these distributed systems for real, right? We've been distributing systems for a long time, but now we're saying like, okay, no, this time for real, we're building distributed systems. And when we talk about those distributed systems, now we're using other special words around how we show they're distributed. They're systems, but they're autonomous systems. And these autonomous systems collaborate with other things within that system. And they're all distributed in their services, and they're microservices, but maybe they're macro services, or maybe we're not going to use any word to describe them. They're just right-sized services, right? And this idea of autonomy, it's very important when you talk about distribution, and I'm going to get into that. So autonomy meaning you're self-governed. And as we build different parts of the system, we want to make sure that all the systems are self-governed, and that's for a couple of reasons. One, when you're autonomous, you can make special decisions independently, and you can cooperate and coordinate when you need to in order to solve those problems. So we're self-governing, and although we outsource a lot of things, you know, for example, a government may outsource a lot of stuff, or a country, where I'm from, the US, we outsource a lot of stuff, but we usually don't outsource people running our government, right? We usually don't outsource that to other countries, usually. But there's this cool idea That's also not a new idea, and it's related to that autonomy of your system, autonomy of people, and it's called the promise theory. And what promise theory gives you is this, it's a general theory about how things operate. And it was sort of picked up a lot by the DevOps community and also picked up now in distributed computing. But the idea is that you make promises, but you don't make obligations. And it's a way to understand how we work in a system. So many of you may be thinking, a promise, an obligation, aren't those things really kind of the same thing? Aren't they extremely similar? What's wrong with being obliged to do something? And the problem is, what obligations do is they sort of impose actions across a boundary. Telling someone else to do something is not a good way to guarantee that that thing is going to be done. But if I can promise you that, hey, this is a menu of the things that I can do, and you ask me to do some of that stuff, if I don't do it, then you can hold me accountable for it, right? With obligations, you lose control. You don't know what's going to happen, right? Autonomy, what it does is it allows you to make information local. And when information is local, you can do whatever you need to do in order to make sure that that information is stable, that that information is repaired when things go wrong, that you can make smart decisions about what state you're in and share that information with other people without it being affected by things around you. So what does that sort of mean in the world and in computing? It means that no one can really tell your story better than you can. And I'll talk a little bit more about, let's look at what obligations do versus what promises do. So obligations end up with some unpredictable outcomes. If you oblige someone to do something and you're not sure that they can actually do it, what you end up with is more of divergence in your systems or even in your relationships. But promises converge, and we call that point of convergence actually idempotence. And when we've reached that desired outcome, we don't do anything else. So what is decreased certainty in real life? Say you get pulled over by the cops, and it's 4 of you in a car, and a cop asks, hey, what's going on? Only one person should talk at that point. If more than one person talks at that point, whatever story you were going to tell can diverge into anything. This story turns into something wild and crazy. But if one person talks and tells the story and tells what's going on, either that person is going to rescue everybody out of the situation, or that person's going to take their own poison pill and take themselves out, right? And then you've got a chance witnessing them leave with their poison pill to answer the question right the next time, right? Okay, no, you're wrong. That's not what happened. You're going away. Now, what happened? The next person has a little more information to speak clearly about. So an autonomous service, what it does is it allows you to promise your own behavior and control that without letting anyone else control that to impact that, and it still allows you to collaborate. So this is a lot of theory. There's a lot of theory around this, promise theory, and in Search for Certainty, and Pat Helland's papers on distributed computing. There's a lot that talks about there. But how do you actually get there in real life? And a lot of my background comes from taking stuff that seems like it's very academic or it's new and it's emerging, and actually helping to apply that stuff in real life to companies who need to deliver stuff to their clients. So let's take a step back and talk about how we used to distribute systems. And we call these our heritage distributed systems. And this is sort of just a super basic picture of what things would look like. Back in the good old days, we'd take maybe some e-commerce site, and we put it on a web application server, and then we put like multiple of them on a web application server, and we put a bunch of those web application servers somewhere, and then we'd use stuff like sticky sessions in monolithic databases, and we'd have to buy some very expensive software for managing your application servers. Not going to name any people, but that's how we did. They were distributed technically, right? And a lot of times you hear people say like, oh, you can't build a monolith because it won't scale. And you can't do this because it won't scale and you won't be able to use it and it's a single point of failure and blah, 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 blah. But the honest truth is, the way this really works is it scales, but it scales at a cost. And it also fails at a very large cost. So what we're looking to do is not just scale, but we're looking to reduce the cost of scaling. The cost of scaling and the cost of failure, the frequency of failure, and how we recover from our failures. So enter distributed scaling at a lower cost. Not brand new, we're distributed scaling. No, we're just doing it at a lower cost. And the first thing people thought to do was, well, not maybe the first thing, but the first thing that was sort of semi-useful was scaling by making things stateless. And we say, oh, we're going to make some things stateless. And there are a lot of players in this field who came out with some tools that say, oh, we'll just make a stateless application. We could take requests so much faster now, but we don't realize that we just push that state somewhere else. So there's really no such thing as stateless. It's like when I was young and someone would say, eat your broccoli. And the way I would eat it is just move it around on the plate. I am eating it. Moving it around on the plate. That's kind of how we treat state in our systems, right? We're like, and so we say, okay, what I'm going to do is I'm going to take this data and I'm going to give every service its own data. We fixed it, right? But no, we probably didn't actually fix it. There's more to the story because remember when we had that monolithic database and we had these shared domain objects that sort of went across your entire system. And they had stuff like ORMs, like Hibernate and MyBaddest and stuff like that help you to make sure that everybody had everything about your domain object that was unnecessary and maybe necessary and didn't have true context. We just threw all that stuff around and made it really, really sticky. So this is problematic. And what happens is when you start upgrading your systems, you start building a system that's supposed to be, hey, this is the new version of our distributed system. We're breaking down the monolith. What we're going to do is we're going to take this stuff that existed here, and we're just going to take it all out and lift and shift. But it's probably not an accurate way to describe your domains if you're really trying, if you're really trying to build autonomous systems. So what we think about instead is not the things, but we're thinking about the things that happen within a system. When we're trying to decide the boundaries, when we're trying to decide how do we determine who can promise what, we want to look at the things that are happening. We want to look at the facts around your boundaries. So we define these events, and we define them as facts. And we sort of call this, event-first domain-driven design now. And I'm sure there were other names for it, and maybe new names will come up for it, but event-first domain-driven design is sort of the thing to do right now to discover the boundaries of your systems. So before you realize we had something that says shop and cart and typical things that you'd find in an e-commerce thing. And instead of thinking about it in terms of the shop service, we'd probably want to think about the events that happen in a shopping context instead. Because when I'm a user, say I'm a domain person, I'm a user in a shopping context, there are going to be things about me that are important to me when I'm in that context that are not important when I'm in the cart context, for example. So what about state? Are we still pushing that around on the plate somehow in this world? Well, first, I'm going to tell you a true story. So how many of you have heard of event sourcing before? You've heard sort of a talk about this. And a lot of times you hear this event sourcing talk and someone talks about eventual consistency and they talk about a bank or a shopping cart. You've heard this example, right? But we all know that that's like somewhat realistic, but not for real. We're like, where's this mythical bank that's going to take our deposits away? It doesn't really exist yet. But there is an example that you can try right now today This is a true life example of what happens to me if you're willing to fly on an American airline. There is an airline that right now today, if you book a flight, it'll send you an invoice to your email, and it'll collect that invoice on the website. If you change that flight later, say you need to go to a different city or you need to change the timing of that flight, when you do it, it'll say, hey, your flight has been successfully changed, we're going to send an invoice to your email. And they send a letter to your email saying that it was changed, but there's no invoice in that email. So you go back with the ticket number to look up the receipt, and when you look it up, the details of your flight have changed, but the invoice is the old invoice. So when you try to go back and bill this to your company, you're like, hey, they charged me for this. But they're like, well, where's the invoice? Well, I can't get the invoice because it's attached to a different ticket number. And it goes in this weird, crazy cycle. And I actually called the airline and they said, we understand that you want an invoice. If you send $15, we can show you how to get the invoice, blah, 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 blah. And I'm like, no, you never sent me an invoice. If you want a copy of the invoice we sent you, send $15 in a signed document. It's like, this is crazy. And this all happens because they update. They use an update in place instead of actually appending to what happened on my transaction. So enter event sourcing and why this wouldn't be a problem if they were using something sensible. And this really has nothing to do with, what database they're using or anything like that. It's just the fact that they actually modify something, they update it without keeping a record around it. So here we are with Akka Persistence, and here we are with something called distributed state. We said state is something that we have to pay attention to. It doesn't go away. And when we're distributing a system, distributing the stateless part of it is quite trivial. And the only point of the stateless part of the system that you're building is to really generate some commands or to manage querying to your system. But the generation of commands, the request for behaviors, that part is pretty simple to multiply with no thought. With those commands, the way event sourcing works is those commands create either one or more events that need to be persisted and maybe tell somebody else or tell something that those events happen. And the point of those events is to really combine and present a state that these entities can always know about. They can always rebuild this state. They always know the history of what's happened inside of your system. And this is our distributed state. And so in Akka Persistence, we have a couple of key structures and a couple of key ideas that need to be understood. And they're very simple ideas, actually. You start with something called your commands. And in Akka Persistence, we have commands, and we also have something called a read-only command, which is really actually kind of just a query. So it's a little bit weird, but it's a command. Just keep it at the top. And then we have events, and then we have state. So these are three things that you need to have, and they all need to be immutable. This is in Java 8, and so in order to create these immutable classes, I'm using Lombok with the @value. And it has some weird things that happen in the IDE that you'll notice. But if you see this, what this basically means is under the covers, it's an annotation that under the covers makes this thing completely immutable. It gives you a hash and an equals and all that other crap. And so inside your persistent actor, you'll see that you'll have your initial state. You have some interval, what you'll use for a snapshot. So when you see this initial state, it has like an underline thinking that something's wrong, and that's because IntelliJ does not recognize it doesn't run the annotation code. But if you actually compile it, it'll run. This is actually a 20-minute talk, JK. And so the other thing that we have that's a part of this is our persistence ID. So if your snapshot interval, that decides how much do I want to save the state of this entity? And you can do that by number of messages, if it's a high throughput system. If it's low, maybe you do it by a time period. However you decide to do that, you should snapshot. I think by events is good. And then you have this persistence ID, and that has to be unique for each entity, and that's what's used when you rebuild your state, when it exists as a way to find the entity when someone's asking about it, and it's also there to rebuild in case it crashes, and it goes back to your journal to rebuild where that state was. And so now inside of here, and that's, I don't know if this quality is really good to see, but inside of here, you'll see we're using a match builder in order to understand the commands, do some sort of validation that you can do automatically, create some events, and persist those events. Does anyone use Scala at all here? Heard of Scala? So like the Scala equivalent of this would have been just a cute little case or something like that. It would have been way cuter than this. But Java's getting there. And this is like cute enough. So this is what you use in order to do the matching of your events. Then you have this very important part where you do your snapshot save. So what you do is your events are only persisted first, and then you update your snapshot. And so also you have to implement your recovery, and that's also pretty easy. You know that when an event comes through. So part of the recovery in an event sourcing system is that it will replay all the events that ever happened in history that were persisted to your journal. And unless you have some snapshot, then it will replay the snapshot. It will take the snapshot and replay the events from the snapshot. So there. So what does CQRS have to do with any of this? And why do we even bring it along? And part of it is because this world of ours that we live in, it's going to revolve around the events. So I talked about the events being persisted, created, all of that. But what I didn't talk about was how we publish them and why we publish them and why they go to a stream. And that part is the important part around CQRS. When you have your commands and your events and your persistent entity, that's really only dealing with a certain part, which is creating, managing your state, understanding what you're promising, X, Y, and Z. But there's also this read side that has to happen in case people are making queries. So I may save something in one way in the journal, but I don't necessarily want to go searching my journal in case I have a query about what's going on in my system. You can query journals, yes, you can, but it may not always be the best thing, the wisest thing to do. Perhaps your read side representation is better looked at as a graph, or maybe it's better looked at as a relational database. The view can be any type of thing. But what you want to do is take those events from the event stream and use your read side processing internally to create the representation that's best for the queries that you're going to use. And what if you need to share facts outside of your system? So we're talking about a single bounded context so far. And if you add other context to this, if you want to talk outside of your context, if you want to share information or facts with people who care about your world, there's something else that you would do. And this is also around the event stream. So what you'd end up doing is taking your events, putting them on the stream, also publishing them to some distributed pub sub, whichever one you'd like to use. And then your other service would take your read side processing and change it in some other way to represent things about this side. So what's a real example of that? So this is less abstract. If I had a service about me and someone's asking me, oh, how are you doing? And I say, I'm fine. But I'm not really fine. But I just say, I'm fine. And when I saved it into my read side event, I was like, fine. But someone else knows me, and they're like listening to those events, And so they translate it into the actual what Kiki really means service. And you go ask the what Kiki really means service, like, how's she actually doing? Well, for real, she's annoyed about something, but she just said she's fine. Because I saw these events come through, and I translated them in a way that someone else could really understand what was going on. So this is something that you would use because you have one context that I know about, and I'm telling my story, but there's another context, someone else who knows some, maybe they know some sacred geometry about me or something like that. And so what are the implications here? There are some technological and there are some business implications around this thing. The storage system itself becomes additive only. And what happens there is you don't lose information that's critical to being able to determine your state, to being able to tell people what your state is, to being able to fulfill the promises that you say that you can fulfill. Append-only data structures actually distribute a lot easier. There are fewer locks to deal with, and horizontal partitioning across a single key, in the case that you're using a journal with a single key, it's easier. But more importantly, there are some business implications. Maybe not more importantly, technology is cool and it's super important, but when you're talking about business, there's some money involved, right? And so with the business implications, your criteria is tracked from the start as an event stream. And what that means is someone's going to be able to, just to break it down, going to be able to make money off of that. At this point, data is the new gold rush. You can answer questions about your system from the origin. So if you're creating events on all of your commands and you're persisting those events to a journal, there are questions about the system that you could answer from the very beginning or from any special point in time. You can also answer questions that haven't been asked yet. Because you have that information, you've collected all of this information, you know that there are things like someone may have thought of before, like, oh, you know what, I never thought about this, but let me see how I could run and munge these reports. And it turns into a natural audit log. So now you don't have to buy extra auditing software just so that you can get an audit log. These are some of the important implications. So, it looks like we've got just in time for the warning. Any questions so far?
I have one. So I don't know if it's working. Yeah. So what if you have any global invariant that you have to make decisions based on, so when you receive a command, you have to make a decision based on your state. For instance, the typical example is the bank account. You cannot overdraw money, right? So what if you had to make a decision based on a command, whether to allow the transaction to happen or not? And that depends on your current state. What do you handle this situation?
So if I'm understanding correctly, you are saying if the bank has a transaction that depends on the state, it needs to determine whether or not I should let this transaction go through depending on the state.
Yes.
So say you have an entity that's, the account is represented as an entity and that account has some state, which is maybe how much money is in that account.
Yeah, and let's say that your processing is being distributed and you are making decisions all over the place for that particular account. How do you allow for, block this command from happening?
So how to disallow the command from happening in case it's in a state that it shouldn't allow it, is what you're asking?
Yes.
Okay, so this is actually a really good question because this is something that you probably wouldn't want to do, disallow the event from happening. And what you'd really want to do is look at the design of who's managing the state and who can actually repair it. So what we look at doing in situations like this is not preventing a transaction, but actually doing compensating transactions. And what people will say is, you guess and then you apologize later, right? Because it's probably going to end up being less expensive for you to allow people to operate more quickly than to try to prevent every operation from happening. Now, that's not always the case. And what I tend to say, in addition to guess and then apologize and compensate, I say that there's always a time period in between. We talk about eventual consistency, and this is really the topic that we're on. There's always a time period in between where something happens and something needs to be fixed, and a disaster will happen if it's not fixed at that time. So that period between event and disaster is how eventually consistent your system can be, or even that portion of your system can be.
Thank you.
Yeah. Any other questions? Sure.
Hi, thank you very much for your presentation. It's really interesting. But what about if I need more information to make the decisions? Just because I asking you something, the example that you gave, how are you? You said, I'm fine, but I really need to know how are you? The women are like that. I need to know how you are now. So what about if I need more context to make you the right question and make you to give me the information that I need?
Absolutely, that's a good question. What if how I really am is a composition of a number of different states? That is something that can possibly happen. And what we call that is composable identity. And so if you compose a number of different states that I know these will add up and be like how I really feel and what I'm really thinking, and whether or not I think I'm going out to dinner again or not with you, then you need to compose all of that stuff together into a composable identity, a composable state. And you could use individual state objects to do that.
Sorry, but from where? Because I don't know who are or from where I have to pick up that information. That's my what are the contexts to give me that information? The context. I need context, to.
Yeah.
To
so
know
if that's going to depend on the system that you've developed. So if I've developed a system to understand me, and I know that part of that system has, what I said, what someone else said, maybe something observing me also saw something like that, you can ask all three of those systems. You could ask from all three of those contexts and get the information from those contexts, and then you have to make a decision on what the truth actually is. Yeah?
Okay, I have a question about publishing the events. When do you do that? Is it during when you are saving, persisting the events, or?
Yeah.
Okay.
So after you've persisted the event and it's truly a fact, then you publish and you update the state of your entity.
But what if you have actually, after you submit your events or persist your events, while you are publishing, you have an exception or something like that under the layer that is responsible for publishing? Sure.
There's something I didn't show. There are also some on persist error or on such and such errors. Like, there are things that you have to do. But there are some things that we can't control. So the way that the journaling works, each type of journal plugin has to have a way to manage failures when we try to persist something. And some of them may do it a little bit differently than others. And so you really need to understand how your journaling layer works in order to understand what you need to do on a persist error, for example. Other questions?
So let's say this. When you are persisting your events, maybe you're creating so much data that you at some point want to get rid of the old events.
Yeah.
After all, you have snapshots, right?
Right.
So how do you manage this? If your data retention policy is based on time and your snapshotting policy is based on the number of events, how do you reconcile these together? So,
well, that's also a really good question. So how are we reconciling if I'm snapshotting based on time and my journal is cleaning up based on size or number of events? Then we may have a problem, because what if I have a spike in events and goes beyond the time that it needs to be cleaned up. The first thing there is, hopefully, you have within your bounded context data that you own, and so you have some level of control or at least knowledge about the system that you're working with, the journal that you're working with. So instead of building something that already is not really in sync with your data retention, you would probably build something that is. If you don't have control of that, or suddenly you thought you had control and someone switched it up on you, then you have to make some different decisions about how you're going to handle cleaning up the data.
So if there is no more questions, we'll finish. Thank you very much, Kiki.
Thank you.